All right, let's take a look at 9.1. Okay, so in 9.1, we're going to talk about estimating a population proportion. So we kind of, in 8.2, we introduced the idea of the population proportion, right? The proportion or percentage of individuals with a certain characteristic, right? And today we want to talk about estimating it. So what we found out in chapter 8 is that we looked at the sampling distribution of the sample mean, x bar, and the sampling distribution of the sample proportion, p hat. And assuming that certain criteria are met, they're both normally distributed, regardless of the underlying distribution, which is pretty cool. That means that we can use the normal calculator to compute probabilities of all of these things. In chapter 9, we're going to discuss how to estimate a population parameter, such as p, mu, or sigma, based on a sample statistic, such as p hat, x bar, or s. Okay. In this section, we're going to talk specifically about the proportion p. Okay? And just by way of reminder, actually, we're using a different phrase for it now, but a point estimate is the value of a statistic that estimates the value of a parameter. P is the proportion of individuals in a population that possess some trait. The point estimate for P is the sample proportion P hat. And we calculate P hat by counting up the number of individuals who are successes and dividing by the total number of individuals in the sample, right? We've talked about this fact before, but what's new here is that we're calling P hat, our sample proportion, we're calling that a point estimate for our population proportion P, okay? So for example, in the textbook, you might see questions like this. In a recent survey of 150 households, 54 had central air conditioning. Find a point estimate for the proportion of households with air conditioning. So the point estimate would be P hat, x over n. Okay? In this particular survey, there were 150 households, so that's our sample size, 150. And out of those 150, 54 of them had central air conditioning. So it's 54 out of 150. Which comes out to 0.36. Okay, so there's the point estimate for our population parameter. Okay. All right. However, this is just based on this one particular sample. If we were to take a different sample of 150 different households, we would probably get a sample proportion that's a little bit different than that, right? Due to that variability, right? So due to this variability in the sample proportion P hat, we need to report a range or an interval of values that estimate P. So in example 1, since P hat was equal to 0.36, we could say that P is equal to 0.36, give or take 0.05, right? So if P hat, our sample proportion, is 0.36, then we could say the true population proportion is probably pretty close to 0.36. It's probably 0.36, give or take a little bit. Mathematically, this could be written in a couple of different ways. We could rewrite it as 0.36 plus or minus 0.05. Or we could actually do the addition and subtraction. We could say 0.36 minus 0.05 is 0.31. 0.36 plus 0.05 is 0.41. Okay, or another way that we could write it, and this is the way that I'm going to ask you to write it, is to actually write it as an interval. So you would say 0.31, 0.41. That's the interval notation for the answer. So you always put the small answer on the left and the big answer on the right. Anyway, this kind of report is called a confidence interval. This 0.05 in our confidence interval here is called the margin of error. And the 0.36, of course, we already talked about, that's our point estimate. So in general, confidence intervals have the form point estimate plus or minus margin of error. Okay. Now for our margin of error, I just kind of randomly chose 0.05. Where did that come from? What good is it? How confident are we that this interval that we're reporting actually contains the true population proportion? These are all questions that we want to be able to answer, right? So you may note that even though we've reported an interval now, there's still a chance that our confidence interval does not contain the true population proportion. If we wanted to increase the probability that our interval contains the population proportion, we should increase the size of our interval. To do that, we would need to increase the margin of error. Okay, so the larger the margin of error, the more certain we are that our interval actually contains the true population proportion. But of course, there's some give and take there, right? Because we don't want to have a huge margin of error, because if we had a huge margin of error, then it wouldn't really narrow down very well what the true population proportion is, which would be kind of a bad thing, right? So we'll talk about that balancing act a little bit more on page 2. Let me start a new video.